When you step outside on a clear night and look up at the twinkling stars scattered across the dark canvas of space, you might think you are seeing the universe as it exists right now, in this very moment. But here is something truly extraordinary that will change how you view every single point of light in the night sky. You are not seeing the present at all. You are looking directly into the past. Every photon of light that reaches your eyes tonight began its journey years, decades, centuries, or even millions of years ago. That bright star you are admiring might have already died, its light still traveling through the vast emptiness of space to reach you. The galaxy you glimpse through a telescope might show you events that happened when dinosaurs roamed the Earth, or even before our planet existed at all. This is not science fiction or a philosophical thought experiment. This is the fundamental reality of how light works in our universe. Light, the very thing that allows us to see and understand everything around us, has a speed limit. It travels at approximately 299,792 kilometers per second through the vacuum of space. While this might seem impossibly fast, the universe is so incredibly vast that even light takes time to cross these enormous distances. Think about what this means for a moment. When you look at the sun during the day, you are seeing it as it was about 8 minutes ago. The light from our nearest star takes 8 minutes to travel the 150 million kilometers between the sun and Earth. If the sun suddenly disappeared right now, we would continue to see it shining in the sky for another 8 minutes before darkness would fall. But this time delay becomes even more dramatic when we look beyond our solar system. The light from the nearest star to our sun, Proxima Centauri, takes over 4 years to reach us. When we observe distant galaxies through powerful telescopes, we are seeing them as they appeared millions or billions of years ago. We are literally looking back through time. This creates one of the most profound realizations in all of science. Because light takes time to travel, we can never truly see the universe as it exists right now. We can only see the universe as it was. Every observation we make, from the closest planet to the most distant galaxy, is a glimpse into cosmic history. The night sky is not just a collection of stars and planets. It is a vast museum of the past, with each point of light representing a different moment in the history of the universe. Tonight, as we explore this incredible concept together, we will journey through space and time to understand how the finite speed of light shapes everything we know about the cosmos. We will discover how this simple fact about light has revolutionized our understanding of time itself, space, and our place in the universe. We will see how looking out into space is the same as looking back in time, and how this cosmic time travel is happening every single time we lift our eyes to the stars. The universe is vast beyond imagination, filled with billions of galaxies, each containing billions of stars. But because of the way light works, when we observe this cosmic symphony, we are not seeing a single moment frozen in time. Instead, we are seeing a layered history, with nearby objects showing us the recent past and distant objects revealing the ancient past. It is as if the universe is constantly sending us postcards from different eras, each one taking a different amount of time to reach us. So the next time you look up at the night sky, remember that you are not just stargazing. You are time traveling. You are seeing the universe not as it is, but as it was. And in that ancient light, carried across unimaginable distances and delivered to your eyes tonight, lies the story of cosmic history itself. To understand why we are always seeing the past when we look into space, we must first explore one of the most fundamental constants in our universe, the speed of light. This is not just any ordinary speed. It represents the ultimate speed limit of reality itself, a cosmic boundary that nothing in the universe can cross. Light travels at exactly 299,792,458 meters per second in the vacuum of space. To put this incredible speed into perspective, light could circle our entire planet Earth more than 7 times in just 1 second. It could travel from New York to Los Angeles in about 16 thousandths of a second. In the time it takes you to blink your eye, light could travel approximately 30,000 kilometers. Imagine if you could travel at the speed of light. You could reach the moon in just over 1 second. You could visit Mars in about 4 minutes when it is closest to Earth. You could journey to the outer edge of our solar system in about 11 hours. Yet even at this tremendous speed, it would still take you over 4 years to reach the nearest star beyond our sun. Yet despite this almost incomprehensible speed, light is not instantaneous. This simple fact has profound implications for how we perceive the universe and our place within it. When we say that light has a finite speed, we mean that it takes time for light to travel from one place to another, no matter how fast it moves. This discovery was not always obvious to humanity. For thousands of years, people believed that light traveled instantaneously. Ancient Greek philosophers debated whether vision worked by light entering the eye or by the eye sending out rays to illuminate objects. But they never questioned whether light itself might have a measurable speed. When you lit a candle in a dark room, the light seemed to fill the space immediately. When the sun rose in the morning, its light appeared to reach Earth without any delay. It was not until the late 1600s that scientists began to suspect that light might have a measurable speed. The first hints came from careful astronomical observations. Early astronomers noticed tiny discrepancies in the timing of celestial events that could not be explained by the motion of the planets and stars alone. These small differences in timing would later prove to be the key to unlocking one of the universe's most important secrets. The first successful measurement of light speed came from an unlikely source, the observation of Jupiter's moons. In 1676, a Danish astronomer named Ole Rømer was studying the eclipses of Io, one of Jupiter's largest moons. As Io orbited around Jupiter, it would periodically disappear behind the giant planet, creating predictable eclipses that astronomers could time with great precision. Rømer noticed something peculiar. The moons of Jupiter seemed to orbit faster when Earth was moving toward Jupiter in its orbit around the Sun, and slower when Earth was moving away from Jupiter. The eclipses would occur several minutes earlier than predicted when Earth was approaching Jupiter, and several minutes later when Earth was moving away. At first, this observation puzzled astronomers. Some suggested that Jupiter's gravity might be affecting time itself, causing the moons to speed up or slow down in their orbits. Others proposed that there might be some unknown force acting on the Jupiter system, but Rømer had a different idea, one that would revolutionize our understanding of light and time. Rømer realized this was not because the moons were actually changing their orbital speed, but because the light carrying information about their positions was taking different amounts of time to reach Earth, depending on the distance between the two planets. When Earth was closer to Jupiter, the light had a shorter distance to travel, so the eclipses appeared to happen sooner. When Earth was farther from Jupiter, the light had to travel a greater distance, causing the eclipses to appear delayed. This was a revolutionary discovery. It meant that light, which seemed to travel instantly in our everyday experience, actually had a finite speed that could be measured and calculated. More importantly, it meant that the information we receive from distant objects in space is not current information. It is historical information, delayed by the time it takes light to travel across the intervening space. Using his observations of Jupiter's moons and the changing distance between Earth and Jupiter throughout the year, Rømer calculated that light traveled at approximately 214,000 kilometers per second. While this was not as accurate as modern measurements, it was remarkably close for the technology available in the 17th century. More importantly, it proved that light had a finite, measurable speed. This discovery opened up entirely new ways of thinking about the universe. If light took time to travel, then everything we saw in the night sky was necessarily a view of the past. The farther away an object was, the further back in time we were seeing it. This meant that the universe was not just vast in space, but also deep in time, with every observation carrying information from a different moment in cosmic history. The speed of light is not just important for understanding astronomy, it is woven into the very fabric of space and time itself. In the early 1900s, Albert Einstein proposed his theory of special relativity, which revealed that the speed of light in a vacuum is the same for all observers, regardless of their motion. This might sound like a simple statement, but it leads to some of the most mind-bending consequences in physics. According to Einstein's theory, space and time are not separate entities, but are interconnected in what physicists call space-time. The speed of light represents the speed at which information can travel through this space-time fabric. It is not just the speed of light particles, but the speed of causality itself. Nothing can travel faster than light because nothing can carry information or influence from one place to another faster than this cosmic speed limit allows. When objects approach the speed of light, remarkable things begin to happen. Time itself begins to slow down relative to stationary observers. Space contracts in the direction of motion. Mass increases toward infinity. These effects, known as time dilation and length contraction, become more pronounced as speeds approach the cosmic speed limit. This is why nothing with mass can ever reach or exceed the speed of light. It would require infinite energy to accelerate any material object to light speed. But light itself is special. Photons, the particles of light, have no mass. This allows them to travel at the cosmic speed limit without violating the laws of physics. In fact, photons must travel at the speed of light. They cannot slow down or speed up. From the moment they are created until the moment they are absorbed, photons move through space at exactly 299,792,458 meters per second. Think about what this means for a single photon's journey through space. A photon created in the core of a distant star begins an epic voyage that may last millions or billions of years. It travels through the vacuum of space, unchanged and undimmed, carrying with it information about the conditions that existed when and where it was born. That photon might journey across vast cosmic distances, through regions of space that contain virtually nothing, past other stars and planets and galaxies, until finally, after eons of travel, it arrives at Earth and enters your eye as you gaze up at the night sky. This constant speed of light creates what we might think of as a cosmic postal system. Every star, every galaxy, every cosmic event sends out messengers in the form of photons. These messengers carry information about what was happening at their source when they were created. But unlike an instant message or phone call, these cosmic messages take time to be delivered. The farther the source, the longer the delivery time. Consider what this means for our observations of the universe. When we look at a star that is 100 light years away, we are seeing that star as it appeared 100 years ago. The light we observed tonight left that star in 1925. If that star exploded 50 years ago, we would not know about it yet. We would have to wait another 50 years for the light from that explosion to reach us. This creates a fascinating paradox in our understanding of cosmic events. Somewhere in the universe right now, stars are being born in stellar nurseries, planets are forming around young stars, and galaxies are colliding in spectacular cosmic dances. But we cannot see any of these present moment events if they are happening at great distances from us. We can only see them after their light has had time to travel across space to reach us. This time delay affects everything we observe in space. The Moon, our closest celestial neighbor, appears to us as it was about 1 3/10 seconds ago. The planets in our solar system appear as they were minutes or hours ago, depending on their distance from Earth. Mars appears as it was between 4 and 24 minutes ago, depending on where both planets are in their orbits. Jupiter appears as it was between 33 and 54 minutes ago. The nearest stars appear as they were years ago. Distant galaxies appear as they were millions or billions of years ago. The speed of light is truly the universal speed limit, and this limit shapes our entire perception of the cosmos. It means that the present moment, as we experience it here on Earth, cannot be shared with the rest of the universe. There is no universal now that extends across space. Instead, our view of the universe is necessarily a view of the past, with different regions of space showing us different moments in cosmic history. This is not a limitation of our instruments or technology. Even with the most advanced telescopes and detection equipment, we cannot see the universe as it exists right now. We can only see it as it was, layer upon layer of cosmic history stretching back through time. The speed of light ensures that when we look out into space, we are always looking back in time, creating a natural time machine that allows us to study the history of the universe itself. Light is the fastest thing in the universe, yet it is not instant. It takes time, and in that time, the universe changes, meaning we are always looking at the past when we observe anything beyond our immediate surroundings. This fundamental truth about light and time opens up one of the most profound realizations about our place in the cosmos. We are not just observers of space, but travelers through time, witnessing the unfolding story of the universe one photon at a time. The speed of light is not just important for understanding astronomy. It is woven into the very fabric of space and time itself. According to Einstein's theory of special relativity, the speed of light in a vacuum is the same for all observers, regardless of their motion. This might sound like a simple statement, but it leads to some of the most mind-bending consequences in physics. When objects approach the speed of light, time itself begins to slow down relative to stationary observers. Space contracts in the direction of motion. Mass increases toward infinity. These effects, known as time dilation and length contraction, become more pronounced as speeds approach the cosmic speed limit. This is why nothing with mass can ever reach or exceed the speed of light. It would require infinite energy to accelerate any material object to light speed. But light itself is special. Photons, the particles of light, have no mass. This allows them to travel at the cosmic speed limit without violating the laws of physics. In fact, photons must travel at the speed of light. They cannot slow down or speed up. From the moment they are created until the moment they are absorbed, photons move through space at exactly 299,792,458 meters per second. This constant speed of light creates what we might think of as a cosmic postal system. Every star, every galaxy, every cosmic event sends out messengers in the form of photons. These messengers carry information about what was happening at their source when they were created. But unlike an instant message or phone call, these cosmic messages take time to be delivered. The farther the source, the longer the delivery time. Consider what this means for our observations of the universe. When we look at a star that is 100 light years away, we are seeing that star as it appeared 100 years ago. The light we observe tonight left that star in 1925. If that star exploded 50 years ago, we would not know about it yet. We would have to wait another 50 years for the light from that explosion to reach us. This time delay affects everything we observe in space. The Moon, our closest celestial neighbor, appears to us as it was about 1 3/10 seconds ago. The planets in our solar system appear as they were minutes or hours ago, depending on their distance from Earth. The nearest stars appear as they were years ago. Distant galaxies appear as they were millions or billions of years ago. The speed of light is truly the universal speed limit, and this limit shapes our entire perception of the cosmos. It means that the present moment, as we experience it here on Earth, cannot be shared with the rest of the universe. There is no universal now that extends across space. Instead, our view of the universe is necessarily a view of the past, with different regions of space showing us different moments in cosmic history. This is not a limitation of our instruments or technology. Even with the most advanced telescopes and detection equipment, we cannot see the universe as it exists right now. We can only see it as it was, layer upon layer of cosmic history stretching back through time. The speed of light ensures that when we look out into space, we are always looking back in time, creating a natural time machine that allows us to study the history of the universe itself. Now that we understand that light has a finite speed, let us embark on a cosmic journey to explore exactly how long it takes for light to travel from various objects in the universe to reach our eyes here on Earth. This journey will take us from our immediate solar neighborhood to the very edges of the observable universe, revealing the incredible scales of space and time that surround us. Let us begin our journey close to home with the light from our own sun. Every morning, when you see the sun rising over the horizon, you are witnessing light that began its journey from the sun's surface approximately 8 minutes and 20 seconds earlier. This means that if something dramatic were to happen to the sun right now, we would continue to see it shining normally in the sky for another 8 1/3 minutes before we would notice any change. But the sun's light does not begin its journey at the surface. Deep within the sun's core, nuclear fusion reactions are constantly creating new photons of light. However, these newborn photons do not immediately escape into space. Instead, they begin an incredible journey through the dense layers of the sun itself. As these photons travel outward from the core, they are constantly absorbed and re-emitted by the hot plasma that makes up the sun's interior. This process of absorption and re-emission causes the photons to take a random walk through the sun's interior, bouncing around in all directions like a pinball in a cosmic machine. Scientists estimate that it takes anywhere from 10,000 to 170,000 years for a photon created in the sun's core to finally reach the surface and escape into space. Only then does it begin the relatively quick 8-minute journey to Earth. This means that the sunlight warming your face today actually began its journey in the sun's core when human civilization was just beginning to develop agriculture, or perhaps even earlier when our ancestors were still living in small hunter-gatherer communities. The light itself carries information from the sun as it existed just 8 minutes ago, but the energy in that light has been trapped inside the sun for millennia. Moving outward from the sun, let us consider the light from other objects in our solar system. The moon, our closest celestial companion, appears to us as it existed about 1 3/10 seconds ago. This might seem like an insignificant delay, but it has practical implications. When the Apollo astronauts were communicating with mission control on Earth, there was a noticeable delay of nearly 3 seconds between question and answer because radio waves, which travel at the speed of light, had to make the round trip between Earth and the moon. The planets in our solar system each appear to us at different moments in the past, depending on their distance from Earth. Venus, our closest planetary neighbor, can appear as it was anywhere from 2 to 14 minutes ago, depending on where both planets are in their respective orbits around the Sun. When Venus is on the opposite side of the Sun from Earth, its light takes much longer to reach us than when it is on the same side of the Sun as Earth. Mars presents an even more dramatic example of cosmic time delay. When Mars is closest to Earth in its orbit, we see it as it was about 4 minutes ago. But when Mars is on the opposite side of the Sun from Earth, we see it as it appeared nearly 24 minutes ago. This variation in light travel time has real consequences for space exploration. When NASA sends commands to rovers on Mars, they must wait anywhere from 4 to 24 minutes to receive confirmation that their commands were received and executed. Jupiter, the giant of our solar system, appears to us as it existed between 33 and 54 minutes ago, depending on the relative positions of Earth and Jupiter in their orbits. The outer planets show us even more distant moments in time. Saturn appears as it was between 1 hour and 7 minutes to 1 hour and 24 minutes ago. Uranus shows us light that is between 2 hours and 37 minutes to 3 hours and 9 minutes old. Neptune, the most distant planet in our solar system, appears as it was between 4 hours and 4 minutes to 4 hours and 29 minutes ago. These time delays might seem small compared to the vast scales we will encounter as we journey beyond our solar system, but they represent our first real encounter with the concept that distance equals time when we observe the universe. The farther we look, the further back in time we see. At the edge of our solar system lies the heliopause, the boundary where the sun's influence gives way to interstellar space. Light from this region takes about 17 hours to reach Earth, meaning we see the edge of our cosmic neighborhood as it appeared nearly a full day ago. Now let us take the giant leap beyond our solar system to the realm of the stars. The nearest star to our sun is Proxima Centauri, located about 4 2/10 light years away. This means that the light we see from Proxima Centauri tonight left that star over 4 years ago, in early 2021. If Proxima Centauri had suddenly flared up or dimmed dramatically last year, we would not know about it yet. We would have to wait until 2028 to see the light from that event. Alpha Centauri, the bright star system that includes Proxima Centauri, appears to us as it existed 4 4/10 years ago. Sirius, the brightest star in our night sky, shows us light that is 8 6/10 years old. By the time we observe Sirius tonight, we are seeing it as it appeared when you were nearly 9 years younger than you are now. Vega, the beautiful blue-white star that serves as the northern pole star in some ancient cultures, appears to us as it was about 25 years ago. The light reaching your eyes from Vega tonight began its journey in the year 2000, around the time when the world was celebrating the new millennium. Arcturus, one of the brightest stars visible from Earth, shows us light that is 37 years old, dating back to 1988. As we look at more distant stars, we encounter light that has been traveling for decades, centuries, and even millennia. The North Star, Polaris, which has guided navigators for thousands of years, appears to us as it was 433 years ago. The light we see from Polaris tonight began its journey during the late 1500s, when Shakespeare was writing his greatest plays and the first European settlements were being established in the Americas. Some of the brightest stars in our night sky are actually supergiants located hundreds or thousands of light years away. Betelgeuse, the reddish star that marks the shoulder of the constellation Orion, is approximately 700 light years distant. When we look at Betelgeuse tonight, we are seeing it as it appeared in the year 1325, during the height of the medieval period on Earth. The light from Betelgeuse that reaches us tonight began its journey when the Aztec Empire was flourishing in Central America and the Renaissance was still centuries in the future. Rigel, the brilliant blue star that marks Orion's foot, is even more distant at about 860 light years away. The light from Rigel that we observe tonight started its journey toward Earth in the year 1165, during the time of the First Crusade. This ancient light has been traveling through space for nearly 9 centuries, carrying with it information about a star as it existed when medieval knights were riding across Europe. But individual stars are just the beginning of our cosmic time journey. As we turn our attention to star clusters, nebulae, and other deep sky objects, we encounter light that has been traveling for thousands and tens of thousands of years. The Pleiades star cluster easily visible to the naked eye as a small fuzzy patch in the constellation Taurus, appears to us as it existed about 444 years ago. The Orion Nebula, a stellar nursery where new stars are being born, shows us light that is about 1,344 years old. When we observe this beautiful cosmic cloud tonight, we are seeing it as it appeared during the early medieval period, when the Byzantine Empire was at its height and the Islamic Golden Age was beginning to flourish. Moving beyond individual objects, we begin to encounter the concept that astronomers call look-back time. This is the idea that the farther we look into space, the further back in time we are seeing. Every increase in distance corresponds to an increase in the age of the light we observe. This creates a natural archaeological record of the universe, with nearby objects showing us the recent cosmic past and distant objects revealing the ancient cosmic past. Within our own Milky Way galaxy, we can observe stars and nebulae that show us light from thousands and tens of thousands of years ago. The center of our galaxy, hidden behind clouds of dust but visible in infrared light, appears to us as it existed about 26,000 years ago. This means we are seeing the galactic center as it was when early humans were creating the first cave paintings and developing complex language. As we prepare to journey beyond our own galaxy, we encounter one of the most profound realizations in astronomy. The light from distant galaxies has been traveling for millions, hundreds of millions, and even billions of years to reach us. When we observe these cosmic islands of stars, we are not just looking across vast distances in space, we are looking back across vast expanses of time, witnessing the universe as it existed in different epochs of cosmic history. Every photon of light carries with it a snapshot of a moment in time. The farther it travels, the further back in time we are looking. But what does that mean for our understanding of the universe? As we continue our journey through cosmic space and time, we will discover that this simple concept opens up extraordinary windows into the past, allowing us to witness the birth of stars, the formation of galaxies, and even the earliest moments after the Big Bang itself. As we have discovered in our cosmic journey, every photon of light is a messenger from the past, carrying information across vast distances and delivering it to us after traveling for seconds, minutes, years, or even eons through space. Tonight, let us explore more deeply what it truly means to always be seeing the past when we observe the universe, and how this fundamental truth transforms our understanding of cosmic history and our place within it. When you step outside and look up at the night sky, you are not simply observing a collection of distant objects. You are witnessing a vast museum of time, where each point of light represents a different moment in the history of the universe. The stars you see are not all shining simultaneously in some cosmic present moment. Instead, they are showing you a layered tapestry of the past, with each star revealing itself as it existed at the moment its light began the journey to your eyes. Consider the constellation Orion, one of the most recognizable patterns in the night sky. When you trace the outline of this celestial hunter with your eyes, you are not seeing all of these stars as they exist at the same moment in time. Instead, you are seeing a collection of snapshots from different periods in history. Betelgeuse, the red giant star marking Orion's shoulder, shows you light from about 700 years ago. Rigel, the brilliant blue star at Orion's foot, displays light that is approximately 860 years old. The three stars of Orion's belt each show you light from different centuries, creating a constellation that exists not in a single moment, but across a span of cosmic time. This realization becomes even more profound when we consider that some of the stars we observe tonight might no longer exist. The massive red supergiant Betelgeuse, for example, is nearing the end of its stellar life and could explode as a supernova at any time. If Betelgeuse exploded 200 years ago, we would not know about it yet. We would continue to see it shining peacefully in Orion's shoulder until the light from that catastrophic explosion finally reached Earth. Only then would we witness one of the most spectacular cosmic events possible: the death of a massive star in a burst of light brighter than an entire galaxy. The light from each star carries with it a detailed record of the conditions that existed when that light was created. The color of a star tells us about its surface temperature. The spectrum of its light reveals the chemical elements present in its atmosphere. The brightness variations in its light can tell us about planets orbiting around it, stellar companions, or changes happening on the star's surface. All of this information is encoded in the light, but it is historical information, sometimes very ancient historical information. When astronomers study a star that is 1,000 light years away, they are essentially conducting an archaeological investigation. They are examining evidence from a time when that star existed 1,000 years ago. If that star has planets, and if one of those planets had developed life, any information about that life would also be 1,000 years out of date. We would be seeing that alien world as it existed during our own medieval period, long before radio telescopes, space travel, or even the printing press existed on Earth. This temporal displacement becomes even more dramatic when we turn our attention beyond individual stars to entire galaxies. Our neighboring galaxy, Andromeda, appears to us as it existed 2.5 million years ago. The light we observe from Andromeda tonight began its journey when our early human ancestors were just beginning to use stone tools, and the first members of the genus Homo were evolving in Africa. In the time it has taken for this ancient light to reach us, our entire species has evolved from primitive hominids to spacefaring beings capable of understanding the very light we are observing. Think about what this means for our observations of Andromeda. If an advanced civilization in that galaxy had built a massive structure or caused some dramatic change to their solar system 2 million years ago, we would just now be seeing the light from that event. Conversely, if astronomers in Andromeda were observing Earth right now, they would see our planet as it existed 2.5 million years ago, long before humans, long before complex life, perhaps seeing only a blue and green world with simple organisms in its oceans. The further we look into space, the deeper we peer into cosmic history. The galaxy Messier 87, home to a supermassive black hole that was recently photographed by the Event Horizon Telescope, appears to us as it existed 53.5 million years ago. The light reaching us from this distant galaxy began its journey when the first primitive mammals were beginning to diversify on Earth, shortly after the extinction of the dinosaurs. Some galaxies are so distant that their light has been traveling for billions of years to reach us. When we observe galaxies that are 10 billion light years away, we are seeing them as they existed when the universe was less than a quarter of its current age. We are witnessing these cosmic islands of stars as they appeared when the Milky Way itself was still a young galaxy, when the first heavy elements were being forged in the cores of massive stars, when the universe was a very different place than it is today. This creates one of the most remarkable aspects of astronomy, the ability to study the evolution of the universe over cosmic time. By observing galaxies at different distances, astronomers can see how galaxies have changed and evolved over billions of years. Nearby galaxies show us what mature galaxies look like today. Distant galaxies show us what galaxies looked like in their youth. By combining observations across these vast distances and time periods, astronomers can piece together the story of how galaxies form, grow, and change over the history of the universe. The light from the most distant galaxies we can observe carries information from when the universe was less than 1 billion years old. These ancient galaxies appear smaller, more irregular, and more actively forming stars than the large, mature spiral and elliptical galaxies we see nearby. They show us a universe in its cosmic adolescence, when galaxy collisions were more common, when star formation was more vigorous, and when the large-scale structure of the universe was still taking shape. But the concept of seeing the past through light extends beyond just galaxies and stars. Every cosmic event we observe happened in the past, and the more distant the event, the further in the past it occurred. When astronomers detect the light from a gamma-ray burst, one of the most energetic events in the universe, they are observing an explosion that happened millions or billions of years ago. The massive star that exploded to create that gamma-ray burst died long before complex life existed on Earth. Yet its final brilliant flash is only reaching us now. Supernova, the explosive deaths of massive stars, provide another dramatic example of how we observe cosmic history through light. Type ER, supernova, which occur when white dwarf stars accumulate matter from companion stars and explode, are so bright that they can be seen across billions of light years. When astronomers observe these stellar explosions in distant galaxies, they are witnessing events that occurred when the universe was much younger. These ancient supernovae have been crucial for discovering that the expansion of the universe is accelerating, driven by the mysterious force we call dark energy. Even more remarkably, some of the light we observe tonight has been traveling since the very early universe. The cosmic microwave background radiation, which we will explore in detail in our next chapter, carries information from when the universe was only 380,000 years old. This ancient light has been journeying through space for over 13.5 billion years, carrying with it a snapshot of the universe in its infancy. The realization that light is a messenger from the past fundamentally changes how we think about time and existence on a cosmic scale. There is no universal present moment that extends across the universe. Instead, every observation we make is an observation of the past, with different regions of space showing us different moments in cosmic history. The night sky is not a snapshot of the universe as it exists now, but rather a vast archive of cosmic memory, with each star and galaxy preserving and displaying a moment from its own past. This means that when we study the universe, we are not just studying space, we are studying time itself. We are cosmic archaeologists, examining light that has been preserved and delivered to us from across the eons. Every photon that enters our telescopes carries with it information about the conditions that existed when and where it was created, allowing us to reconstruct the history of stars, galaxies, and the universe itself. When we look up at the stars, we are not just stargazing. We are time traveling, witnessing the universe not as it is, but as it was. And in that ancient light, carried across unimaginable distances and delivered to our eyes tonight, lies the story of cosmic history itself. Every observation adds another piece to our understanding of how the universe has evolved from its earliest moments to the present day, reminding us that the cosmos is not just vast in space, but deep in time, with every point of light serving as a window into the past. As we continue our journey through cosmic time, we now arrive at perhaps the most remarkable discovery in all of astronomy: the cosmic microwave background radiation, often called simply the CMB. This ancient light represents the oldest photons we can observe in the universe, carrying information from a time when the cosmos was just 380,000 years old, long before the first stars ignited, long before galaxies formed, and billions of years before our solar system even existed. To understand the cosmic microwave background, we must travel back in time to the very early universe, to an epoch so distant that the light we observe from it has been journeying through space for over 13.5 billion years. This light began its journey when the universe was a vastly different place than it is today, when it was hot, dense, and filled with a glowing plasma that pervaded all of space. In the beginning, During the first few 100,000 years after the Big Bang, the universe was far too hot for atoms to exist as we know them today. The temperature was so extreme that electrons could not remain bound to atomic nuclei. Instead, the universe was filled with a sea of free electrons and atomic nuclei, creating what physicists call a plasma. This plasma was completely opaque to light, meaning that photons could not travel very far before being absorbed or scattered by the free electrons. Imagine trying to see through a thick fog so dense that you cannot see your hand in front of your face. This is similar to what the early universe was like for light. Photons would be created and almost immediately absorbed or scattered, creating a glowing, opaque medium that filled all of space. During this time, the universe was dark to any hypothetical observer because light could not travel freely through the plasma. But as the universe expanded, it also cooled. Like a balloon being inflated, the expansion of space caused the temperature and density of the universe to decrease. After about 380,000 years of expansion and cooling, something remarkable happened. The temperature dropped to about 3,000 degrees Kelvin, cool enough for electrons to finally combine with atomic nuclei to form the first neutral atoms, primarily hydrogen and helium. This moment, known as recombination, was one of the most important events in cosmic history. When the free electrons combined with nuclei to form neutral atoms, the universe suddenly became transparent to light. For the first time since the Big Bang, photons could travel freely through space without being immediately absorbed or scattered. The cosmic fog lifted, and the universe became clear. At the moment of recombination, the entire universe was glowing with the heat of its own creation. Every point in space was emitting light with the warm, orange glow of an object heated to about 3,000 degrees Kelvin, similar to the glow of a heating element on an electric stove. This light filled the universe uniformly, creating a cosmic background of thermal radiation that pervaded all of space. From that moment, 13.5 billion years ago, this ancient light began its journey through space. But as the universe continued to expand, something remarkable happened to this primordial glow. The expansion of space itself stretched the wavelengths of these ancient photons, gradually shifting them from visible light toward longer, redder wavelengths. This process, known as cosmological redshift, has continued for billions of years. Today, after more than 13 billion years of cosmic expansion, the light that was once a warm orange glow has been stretched so much that it now appears as microwave radiation, with wavelengths about 1,000 times longer than they were when the light was first emitted. This is why we call it the cosmic microwave background. The ancient light of creation now fills the universe as a faint microwave signal that can be detected with sensitive radio telescopes. The cosmic microwave background represents the most distant thing we can ever hope to observe with light. It is the edge of the observable universe in time, the furthest back we can see using electromagnetic radiation. Beyond this cosmic horizon lies a period when the universe was opaque to light, a time we cannot observe directly because photons could not travel freely through the hot, dense plasma that filled space. The discovery of the cosmic microwave background was one of the greatest triumphs of 20th century astronomy. In 1965, two radio astronomers named Arno Penzias and Robert Wilson were testing a sensitive microwave antenna at Bell Laboratories in New Jersey. They kept detecting a persistent background noise that seemed to come from all directions in the sky. At first, they thought this might be interference from their equipment, or perhaps radiation from the city of New York, or even droppings from pigeons that had nested in their antenna. But after careful investigation, Penzias and Wilson realized they had discovered something extraordinary. The signal they were detecting was not interference or noise. It was the ancient afterglow of the Big Bang itself, the cosmic microwave background radiation that had been predicted by theoretical physicists but never before observed. This discovery provided powerful evidence for the Big Bang theory and revolutionized our understanding of the universe's origin and evolution. The cosmic microwave background is remarkably uniform across the sky, appearing almost exactly the same in every direction we look. This uniformity tells us that the early universe was incredibly smooth and homogeneous, with matter and energy distributed very evenly throughout space. However, the CMB is not perfectly uniform. Sensitive measurements reveal tiny variations in temperature, typically only a few millionths of a degree, across different regions of the sky. These tiny temperature fluctuations in the cosmic microwave background are among the most important observations in all of cosmology. They represent the seeds of all the large-scale structure we see in the universe today. Regions that were slightly denser than average in the early universe would have been slightly warmer, while regions that were slightly less dense would have been slightly cooler. Over billions of years, gravity amplified these tiny differences, causing the denser regions to attract more matter and eventually form the first stars, galaxies, and galaxy clusters. The pattern of these temperature fluctuations in the cosmic microwave background acts like a cosmic blueprint, showing us the initial conditions from which all the complexity of the modern universe emerged. By studying this pattern in exquisite detail, astronomers have been able to determine many fundamental properties of the universe, including its age, composition, and the rate at which it is expanding. One of the most remarkable aspects of the cosmic microwave background is that it provides us with a baby picture of the universe. When we observe the CMB, we are seeing the universe as it appeared when it was only 380,000 years old, less than 0.03% of its current age. At this time, the universe contained no stars, no galaxies, no planets, and no complex structures of any kind. It was simply a smooth glowing gas of hydrogen and helium atoms, cooling as it expanded through space. The cosmic microwave background also tells us about the composition of the universe. The precise pattern of temperature fluctuations reveals that ordinary matter, the stuff that makes up stars, planets, and people, comprises only about 5% of the total energy density of the universe. About 27% consists of dark matter, a mysterious form of matter that does not interact with light, but reveals its presence through its gravitational effects. The remaining 68% is dark energy, an even more mysterious force that is causing the expansion of the universe to accelerate. Modern space-based telescopes have mapped the cosmic microwave background with extraordinary precision. The Cosmic Background Explorer satellite, launched in 1989, first detected the tiny temperature variations in the CMB. The Wilkinson Microwave Anisotropy Probe, which operated from 2001 to 2010, created detailed maps of these fluctuations. Most recently, the Planck satellite, which operated from 2009 to 2013, produced the most precise measurements of the cosmic microwave background ever made. These observations have confirmed our understanding of the Big Bang theory and provided unprecedented insights into the early universe. They have allowed astronomers to determine that the universe is 13.8 billion years old, that it is geometrically flat, and that it underwent a period of rapid expansion called inflation during its first tiny fraction of a second of existence. The cosmic microwave background represents a direct connection to the earliest moments of cosmic history that we can observe. Every time radio astronomers point their telescopes at the sky and detect this faint microwave signal, they are observing photons that have been traveling through space for over 13 billion years. These ancient messengers carry with them information about the conditions that existed when the universe was in its infancy, when it was hot, dense, and glowing with the heat of its own creation. When we think about the cosmic microwave background, we are contemplating light that is older than our solar system, older than our galaxy's spiral arms, older than most of the stars we see in the night sky. This ancient radiation surrounds us at all times, filling every cubic centimeter of space with the faint afterglow of creation. It is always there, a cosmic background that pervades the universe, carrying with it the memory of the moment when light first became free to travel through space. The cosmic microwave background is a glimpse of the universe in its infancy, a snapshot frozen in time from when the cosmos was smooth and simple, before gravity had time to sculpt it into the rich tapestry of stars, galaxies, and cosmic structures we observe today. It reminds us that everything we see in the universe, from the smallest asteroids to the largest galaxy clusters, emerged from incredibly simple and uniform initial conditions. The complexity and beauty of the modern universe grew from the tiny seeds preserved in this ancient light. Tonight, as you contemplate the vastness of space and time, remember that you are surrounded by this ancient light, the oldest photons in the universe, carrying information from the very dawn of time itself. The cosmic microwave background is the most ancient light we can observe, revealing the universe's first moments to us and reminding us that everything we see in the cosmos is always a memory of the past, with this particular memory reaching back to the very beginning of observable time. In our journey through cosmic time, we now turn our attention to one of the most profound and beautiful observations in the history of astronomy, the Hubble Deep Field. This remarkable image, captured by the Hubble Space Telescope, represents humanity's deepest look into the universe, revealing thousands of galaxies whose light has been traveling toward us for billions of years. Each galaxy in this cosmic portrait is a time capsule, showing us the universe as it existed in different epochs of cosmic history, long before our solar system, our planet, or even our galaxy had taken their current form. The story of the Hubble Deep Field begins with a bold decision made by astronomers in the early 1990s. The Hubble Space Telescope had been in orbit for several years, capturing stunning images of nearby celestial objects and revolutionizing our understanding of the cosmos. But astronomers wondered what would happen if they pointed this powerful instrument at what appeared to be an empty patch of sky and stared at it for an extraordinarily long time. They chose a tiny region of space in the constellation Ursa Major, an area so small that it would be covered by a grain of sand held at arm's length. To the naked eye, this patch of sky appeared completely black and empty, devoid of any visible stars or cosmic objects. Most astronomers expected that even with Hubble's extraordinary vision, this region would contain only a few faint, distant galaxies at most. In December 1995, astronomers began their ambitious observation. For 10 consecutive days, the Hubble Space Telescope stared at this seemingly empty patch of space, collecting photons of light that had been traveling across the universe for billions of years. The telescope gathered light for a total of 100 hours, creating the equivalent of an extremely long exposure photograph that could reveal objects far too faint to be seen in shorter observations. When the data was finally processed and the image assembled, astronomers were stunned by what they saw. The tiny patch of supposedly empty sky was actually teeming with galaxies. Where they had expected to find perhaps a dozen faint objects, they discovered nearly 3,000 galaxies of all shapes, sizes, and colors. The image revealed a rich tapestry of cosmic history, with each galaxy representing a different moment in the evolution of the universe. The Hubble Deep Field image shows us galaxies as they appeared when the universe was much younger than it is today. The most distant galaxies in the image appear as they existed when the universe was less than 1 billion years old, showing us cosmic structures from a time when the universe was only about 7% of its current age. These ancient galaxies provide our first glimpse of how the universe looked during its cosmic adolescence, long before it matured into the rich and complex cosmos we observe today. What makes the Hubble Deep Field so remarkable is not just the number of galaxies it revealed, but the incredible diversity of cosmic structures and the vast range of cosmic time it encompasses. The image contains galaxies that appear as they existed at many different epochs in cosmic history. Some galaxies show us light that is relatively recent, from only a few billion years ago. Others reveal light that has been traveling for over 10 billion years, showing us these cosmic islands as they appeared when the universe was still in its infancy. Each galaxy in the Hubble Deep Field tells a unique story of cosmic evolution. The nearest galaxies in the image appear large, well-formed, and similar to the mature spiral and elliptical galaxies we observe in our local cosmic neighborhood today. These galaxies show us the universe as it appeared a few billion years ago, when galaxy formation and evolution had already progressed significantly, and when large-scale cosmic structures had already taken shape. But as we look at more distant galaxies in the image, we begin to see signs of a younger, more chaotic universe. The most distant galaxies appear smaller, more irregular, and more actively forming stars than their nearby counterparts. Many of these ancient galaxies are undergoing dramatic episodes of star formation, creating new stars at rates much higher than we observe in galaxies today. Some appear to be in the process of merging with other galaxies, creating the building blocks of the larger galaxies we see in the modern universe. The colors of the galaxies in the Hubble Deep Field also tell us about their ages and the types of stars they contain. Blue galaxies are typically younger and more actively forming new stars, while red galaxies tend to be older and contain populations of mature stars. The most distant galaxies in the image often appear blue, indicating that they are vigorous star-forming regions where massive, hot, blue stars are being born in great numbers. The Hubble Deep Field image also reveals the hierarchical nature of galaxy formation in the early universe. Many of the distant galaxies appear to be smaller building blocks that would eventually merge and grow to form the large galaxies we see today. This supports the theoretical understanding that galaxies grow over cosmic time through a process of mergers and accretion, with smaller galaxies combining to form progressively larger structures. One of the most profound aspects of observing the Hubble Deep Field is the realization that we are witnessing events that occurred billions of years before Earth even existed. When the light from the most distant galaxies in the image began its journey toward us, our solar system had not yet formed. The sun was not yet born. The heavy elements that make up rocky planets like Earth had not yet been created in sufficient quantities by stellar nucleosynthesis. We are observing a universe that predates not only human civilization, but the very existence of our world. Consider what this means for our understanding of cosmic time. When we look at a galaxy in the Hubble Deep Field that appears as it was 10 billion years ago, we are seeing that galaxy as it existed when the universe was less than 4 billion years old. At that time, the Milky Way was still a young, actively star-forming galaxy, very different from the mature spiral galaxy we know today. The solar system would not form for another 5.5 billion years. Complex life on Earth would not emerge for over 9 billion years. The galaxies we observe in the Hubble Deep Field are so distant that their light has been significantly affected by the expansion of the universe. The cosmological redshift has stretched the wavelengths of their light, shifting what was once visible light toward longer, redder wavelengths. Some of the most distant galaxies can only be observed in infrared light because their visible light has been redshifted beyond what our eyes can see. This is why space-based infrared telescopes like the James Webb Space Telescope are so important for studying the most distant reaches of the universe. The success of the original Hubble Deep Field led to several follow-up observations, each pushing deeper into space and further back in time. The Hubble Ultra Deep Field, captured in 2004, stared at an even smaller patch of sky for over 11 days, revealing galaxies so distant that their light has been traveling for over 13 billion years. These observations show us galaxies as they appeared when the universe was less than 800 million years old, providing glimpses of some of the first large-scale structures to form after the cosmic dark ages. The Hubble Extreme Deep Field, created by combining observations spanning more than 10 years, represents the deepest view of the universe ever captured in visible light. This image reveals galaxies from when the universe was only 400 million years old, showing us cosmic structures from very close to the end of the cosmic dark ages, when the first stars and galaxies were just beginning to illuminate the universe. Each of these deep field observations has revealed new insights about the early universe and the process of galaxy formation and evolution. They have shown us that galaxies began forming much earlier in cosmic history than many astronomers had expected. They have revealed that the early universe was already rich with diverse galactic structures, even when it was less than 1 billion years old. They have provided crucial data for understanding how the simple, smooth universe revealed by the cosmic microwave background evolved into the complex, structured cosmos we observe today. The deep field images also highlight one of the most remarkable aspects of observing the distant universe: the incredible number of galaxies that exist in space. If the small patch of sky observed in the Hubble Deep Field is representative of the universe as a whole, then there are hundreds of billions of galaxies in the observable universe, each containing hundreds of billions of stars. This suggests that there are more stars in the universe than there are grains of sand on all the beaches of Earth. When we contemplate the Hubble Deep Field, we are not just looking at an image of distant galaxies. We are looking at a time machine that shows us the universe in different stages of its evolution. We are witnessing the cosmic story unfold before our eyes, seeing how the universe has changed and evolved over billions of years of cosmic time. Each galaxy in the image is a chapter in this cosmic story, frozen at a different moment in the long history of the universe. The light from these distant galaxies began its journey billions of years ago, when the universe was young and very different from what we observe today. That ancient light has traveled across expanding space, carrying with it information about conditions that existed in the early universe. Tonight, when astronomers point their telescopes toward these distant realms, they are collecting photons that started their journey when the universe was in its cosmic childhood, long before the rich complexity of the modern cosmos had time to develop. Through the Hubble Deep Field, we peer back in time, witnessing galaxies that formed billions of years ago, seeing the universe as it was in its youth, when galaxy formation was more vigorous, when star birth rates were higher, and when the large-scale structure of the cosmos was still taking shape. But what happens when we look even further back in time? What lies beyond even these ancient galaxies? As we continue our journey through cosmic history, we will discover that there are limits to how far back in time we can see, boundaries set by the fundamental nature of light and the expansion of the universe itself. As we have journeyed through the cosmos, following light from nearby stars to the most distant galaxies, we have seen how the finite speed of light allows us to look back through time. But now, we must confront one of the most profound and mysterious boundaries in the universe. Places where light itself can no longer escape, where our ability to see the past comes to an absolute end. These are the event horizons of black holes, regions where space and time become so distorted that even light, the fastest thing in the universe, cannot complete its journey to our eyes. To understand how black holes represent the ultimate limitation of our ability to observe time and space, we must first explore what happens to light when it encounters these cosmic monsters. Black holes are regions of space where gravity has become so intense that it warps the very fabric of space-time itself. They form when massive stars collapse at the end of their lives, compressing matter into such a small space that the escape velocity exceeds the speed of light. Imagine standing at the edge of a cliff so tall that if you dropped a ball, it would need to be thrown upward faster than any speed possible to avoid falling over the edge. A black hole is like this cliff, but for light itself. The event horizon is the boundary around a black hole beyond which even light cannot escape. Once light crosses this invisible boundary, it is doomed to fall toward the center of the black hole, never to return to the outside universe. This creates a fundamental limit to what we can observe. When matter falls toward a black hole, we can watch its journey up until the moment it crosses the event horizon. But once it passes this point of no return, no information about what happens to that matter can ever reach us. The event horizon marks the boundary between the observable and unobservable universe, a cosmic curtain beyond which we can never see. From our perspective as outside observers, something remarkable and disturbing happens when we watch an object fall toward a black hole. As the object approaches the event horizon, the extreme gravitational field causes time itself to slow down relative to our reference frame. This effect, known as gravitational time dilation, becomes more and more pronounced as the object gets closer to the event horizon. To us, watching from a safe distance, the falling object appears to slow down dramatically as it approaches the event horizon. Its light becomes increasingly redshifted, stretched to longer and longer wavelengths by the intense gravitational field. The object appears to freeze at the event horizon, its image becoming redder and dimmer until it fades from view. From our perspective, the object never quite crosses the event horizon. Instead, it appears to be frozen there forever, its light becoming too faint and redshifted for us to detect. But this is just an illusion created by the extreme curvature of space-time near the black hole. From the perspective of the falling object itself, time passes normally, and it crosses the event horizon in a finite amount of time. However, once it crosses this boundary, no signal or information from the object can ever reach the outside universe. The event horizon represents an absolute information barrier, a boundary beyond which no light or information can travel. This has profound implications for our understanding of time and causality in the universe. Inside the event horizon of a black hole, the normal relationship between cause and effect breaks down. The intense gravitational field becomes so strong that it overwhelms all other forces, pulling everything inexorably toward the center of the black hole, the singularity, where the laws of physics, as we understand them, break down completely. Near the event horizon, space and time become so distorted that the concept of now loses its meaning. The curvature of space-time becomes so extreme that light cones, which define the boundaries of cause and effect, tip over completely. Inside the event horizon, all paths through space-time lead toward the singularity. There is no escape, no way for information to travel back to the outside universe. This represents the ultimate limit to our ability to observe the universe through light. No matter how powerful our telescopes become, no matter how sensitive our detectors, we can never see what happens inside a black hole's event horizon. The event horizon marks the boundary of the observable universe in the strongest possible sense. Beyond this boundary, light cannot travel in a way that allows us to perceive it, marking the ultimate limit to observing time and space. But black holes also demonstrate the strange relationship between gravity, light, and time in other ways. Just outside the event horizon, in a region called the photon sphere, light can actually orbit the black hole. At this precise distance, photons can travel in circular paths around the black hole, trapped in an eternal orbit by the balance between their forward motion and the inward pull of gravity. Light that passes closer to the black hole than the photon sphere will spiral inward and eventually cross the event horizon, lost forever to outside observers. Light that passes farther away will be deflected by the black hole's gravity, but will eventually escape to infinity, carrying with it information about its close encounter with one of the universe's most extreme objects. The study of black holes has revealed that they are not just cosmic vacuum cleaners that devour everything in their path. They are dynamic objects that can actually emit radiation through a quantum mechanical process discovered by Stephen Hawking. This Hawking radiation arises from quantum fluctuations near the event horizon, where pairs of particles are created from the vacuum of space. Normally, these particle pairs would annihilate each other immediately, but near a black hole, one particle can fall across the event horizon while the other escapes, carrying away a tiny amount of energy. This process means that black holes actually evaporate over time, losing mass through the emission of Hawking radiation. However, for stellar mass black holes, this process is extraordinarily slow. A black hole with the mass of our Sun would take longer than the current age of the universe to evaporate completely. The most massive black holes, which can contain billions of times the mass of the Sun, would take an almost incomprehensibly long time to evaporate, far longer than any other known process in the universe. The paradoxical nature of black holes extends to the information they contain. When matter falls into a black hole, it carries with it information about its quantum state. According to classical general relativity, this information is lost forever once it crosses the event horizon. But quantum mechanics suggests that information cannot be destroyed, leading to what physicists call the black hole information paradox. This paradox highlights the fundamental tension between our understanding of gravity, as described by Einstein's general relativity, and quantum mechanics. Resolving this paradox may require a new theory of quantum gravity that can reconcile these two pillars of modern physics. Some theories suggest that the information is not actually lost, but is encoded on the event horizon itself, or that it is released back into the universe through the Hawking radiation in ways that we do not yet understand. The event horizons of black holes also serve as natural laboratories for testing our understanding of space-time and gravity. When we observe the effects of black holes on nearby matter and light, we are seeing the predictions of Einstein's general relativity played out in the most extreme conditions possible. The recent direct imaging of black hole event horizons by the Event Horizon Telescope has provided unprecedented tests of our understanding of these cosmic monsters. The supermassive black hole at the center of our galaxy, known as Sagittarius, a star, contains about 4 million times the mass of our Sun, compressed into a region smaller than the orbit of Mercury. When astronomers observe the stars that orbit close to this black hole, they can see the effects of intense gravity on both the motion of the stars and the light they emit. These observations have confirmed many predictions of general relativity and have provided new insights into the nature of space-time near black holes. But perhaps the most profound aspect of black holes is what they tell us about the nature of time itself. Near a black hole, time passes differently depending on your location and motion. An observer falling toward a black hole would experience time normally from their own perspective, but would see the rest of the universe speeding up around them. An outside observer would see the falling observer's time slowing down dramatically as they approach the event horizon. This demonstrates that time is not absolute or universal, but is relative and dependent on the gravitational environment. The extreme conditions near black holes reveal that our everyday experience of time as a steady, uniform flow is just an approximation that works well in the weak gravitational fields we experience on Earth, but breaks down completely in the intense gravitational fields near black holes. The event horizon represents more than just a boundary in space. It represents a boundary in time itself, a point beyond which the future cannot influence the past, where the normal flow of causality breaks down. Inside a black hole, all paths through space-time lead toward the singularity, where space and time themselves may cease to have meaning. When we contemplate black holes and their event horizons, we are confronting the deepest mysteries of space, time, and gravity. These cosmic objects represent the ultimate limits of our ability to observe and understand the universe through light. They remind us that there are boundaries to knowledge, regions of space-time that will forever remain hidden from our view, no matter how advanced our technology becomes. Inside a black hole, light cannot escape. In a way, time itself stops as we know it. What does this tell us about the nature of light and its journey through the universe? It tells us that even light, the cosmic messenger that carries information across vast distances and through billions of years of time, has limits. There are places in the universe where even light cannot complete its journey, where the very concept of observation breaks down, and where the universe keeps its deepest secrets hidden behind the impenetrable veil of the event horizon. As we continue our exploration of how light and time are intertwined throughout the universe, we now encounter one of the most profound and mind-bending concepts in all of physics: the relativity of simultaneity. This principle, discovered by Albert Einstein in his theory of special relativity, reveals that our everyday notion of now is not absolute or universal. Instead, what we consider to be the present moment depends entirely on our motion through space. And different observers moving at different speeds will disagree about whether distant events happen at the same time. To understand this remarkable concept, let us first consider how we normally think about time in our daily lives. When you look at a clock and see that it reads 3 o'clock in the afternoon, you naturally assume that it is 3 o'clock everywhere in the universe at that same moment. When something happens here on Earth right now, you might think that there is a corresponding right now on Mars, on Jupiter, in the nearest star system, and in the most distant galaxies. This intuitive notion suggests that there is a universal present moment that extends across all of space, a cosmic now that all observers in the universe would agree upon. But Einstein's theory of relativity reveals that this intuitive understanding of time is fundamentally incorrect. There is no universal now that extends across space. Instead, the concept of simultaneity is relative, depending on the motion of the observer. Two events that appear to happen at exactly the same time to one observer might appear to happen at different times to another observer who is moving at a different speed. This strange behavior arises directly from the fundamental properties of light and space-time. We have learned that light travels at a finite speed, approximately 300 million meters per second, and that this speed is the same for all observers regardless of their motion. This seemingly simple fact has profound consequences for how different observers experience time and simultaneity. Imagine two observers, Alice and Bob, who are moving relative to each other at a significant fraction of the speed of light. Alice is sitting in a spaceship traveling at high speed, while Bob is standing on a platform that Alice's spaceship passes by. Now suppose that two events happen in the universe. A star explodes in a distant galaxy, and at what appears to be the same moment, a planet is discovered orbiting a nearby star. From Bob's perspective, standing on his stationary platform, these two events appear to happen simultaneously. He sees the light from the distant supernova and receives the signal announcing the planet discovery at exactly the same time, and after accounting for the light travel time from each event, he concludes that they occurred at the same moment in cosmic time. But Alice, traveling at high speed in her spaceship, would observe something very different. Due to her motion through space, she would see these same two events happening at different times. Depending on the direction of her motion relative to the two events, she might see the supernova happen first and the planet discovery later, or vice versa. The faster Alice is moving, the greater the time difference she would observe between these events. This is not just a theoretical possibility or a limitation of measurement techniques. It is a fundamental feature of space-time itself. The relativity of simultaneity means that there is no absolute way to define what at the same time means for events that are separated by large distances in space. The order of events and whether they appear simultaneous depends on the reference frame of the observer. This concept becomes even more remarkable when we consider its implications for our observations of the universe. When we look up at the night sky and see stars scattered across the celestial sphere, we might think we are seeing a snapshot of the universe as it exists at this moment. But the relativity of simultaneity tells us that this is an illusion. Different observers, moving at different speeds, would each construct a different slice through space-time, seeing different combinations of past events as appearing to be simultaneous. Consider what this means for someone traveling at high speed through our galaxy. An astronaut moving at 90% of the speed of light toward the center of the Milky Way would have a very different perception of cosmic simultaneity than we do here on Earth. Events that appear simultaneous to us might be separated by thousands of years in the astronaut's reference frame. The astronaut might see some stars as they were in the past, relative to our observations, while seeing others as they will be in the future, relative to our current view. The relativity of simultaneity also affects how we think about communication across cosmic distances. When we send a radio signal to a distant star system, we naturally think of the moment the signal is sent and the moment it is received as being separated by the light travel time. But observers moving at different speeds would disagree about exactly when the signal was sent and when it was received, even after accounting for light travel time. This has profound implications for any hypothetical galactic civilization. Different members of such a civilization, traveling at different speeds between star systems, would have fundamentally different notions of simultaneity. They would disagree about the timing of events, about what constitutes the present moment across the galaxy, and about the sequence in which distant events occur. The concept of simultaneity becomes even more complex when we consider accelerated motion. An observer who is accelerating experiences an even more dramatic relativity of simultaneity. During acceleration, their notion of what events are happening now in distant parts of the universe changes continuously. An astronaut accelerating away from Earth would see the rate of clocks on Earth appear to slow down, then speed up, then slow down again, depending on the details of their acceleration. The relativity of simultaneity also reveals something profound about the nature of the present moment itself. In our everyday experience, the present seems like a knife edge between the past and the future, a singular moment that exists throughout the universe. But relativity tells us that the present is not a universal moment, but rather a subjective experience that depends on our motion through space-time. This means that the past, present, and future are not absolute categories, but are relative to the observer. Events that are in your future might be in the past for someone moving at high speed relative to you. The universe does not have a single, universal timeline, but rather a complex web of interconnected world lines, each representing the path of an object or observer through space-time. The relativity of simultaneity also affects how we interpret observations of distant cosmic events. When we observe a supernova explosion in a distant galaxy, we are seeing an event that happened millions or billions of years ago in our reference frame. But an observer moving at high speed relative to us might see that same supernova as having happened at a different time relative to other cosmic events they observe. This creates a fascinating puzzle for our understanding of cosmic history. The sequence of events we observe in the universe, the timeline of cosmic evolution we reconstruct from our observations, is not absolute. Different observers moving at different speeds would construct different timelines, with different sequences of events and different notions of which events occurred simultaneously. The speed of light plays a crucial role in the relativity of simultaneity. It is because light has a finite speed and because this speed is the same for all observers, that different observers disagree about simultaneity. If light traveled at infinite speed, or if its speed depended on the motion of the observer, then simultaneity would be absolute. But the finite, constant speed of light ensures that motion through space affects the passage of time and the perception of simultaneity. This connection between light and time runs even deeper. The speed of light is not just the speed at which electromagnetic radiation travels. It is the fundamental speed of space-time itself, the speed at which cause and effect propagate through the universe. It is the speed that connects space and time into the unified fabric of space-time that Einstein revealed in his theory of relativity. The relativity of simultaneity also has implications for our understanding of free will and determinism. If the future for one observer can be the past for another observer, this raises profound questions about the nature of time and causality. Some interpretations of relativity suggest that the entire history of the universe, past, present, and future, exists as a single four-dimensional block of space-time, with the passage of time being merely a subjective experience of conscious observers moving through this block. When we contemplate the relativity of simultaneity, we are forced to abandon our intuitive notions of absolute time and universal simultaneity. The universe does not tick to a single cosmic clock. Instead, time is woven into the very fabric of space, creating a complex tapestry where the perception of now depends on motion, acceleration, and gravity. Our perception of the present moment is relative and always subject to the delay of light. The now we experience is not absolute. The speed of light shapes our perception of the present, making every moment in time a fleeting glimpse of what was. This realization transforms our understanding of time itself, revealing that the universe is far stranger and more wonderful than our everyday experience suggests. The next time you look up at the stars and think about the vast cosmos surrounding us, remember that there is no single, universal now that extends across space. Each observer, depending on their motion through the universe, experiences their own unique slice through space-time, their own personal version of the present moment. The speed of light ensures that our view of the universe is always a view of the past. But relativity tells us that even this past is not absolute. It is relative, subjective, and dependent on our journey through the cosmic dance of space and time. As we have explored the intimate relationship between light and time throughout the universe, we have seen how the finite speed of light creates a natural form of time travel, allowing us to observe the past whenever we look into space. But this raises a fascinating question. If we are already time travelers of sorts, observing ancient light from distant stars and galaxies, could we use our understanding of light and space-time to travel through time more deliberately? What would happen if we tried to break free from our natural journey through time and venture into the past or future? The possibility of time travel has captivated human imagination for centuries, appearing in countless stories, novels, and films. But beyond the realm of science fiction, time travel is also a serious topic of study in theoretical physics. Einstein's theories of relativity, the same theories that explain why we see the universe's past when we look at distant objects, also suggest that under certain extreme conditions, more dramatic forms of time travel might be possible. We have already encountered one form of time travel in our cosmic journey: the fact that we are constantly observing the past when we look at distant objects. When we see the sun as it was 8 minutes ago, or observe galaxies as they appeared billions of years ago, we are already time travelers in the most literal sense. We are seeing events that happened in the past, preserved and delivered to us by the patient journey of light across space. But physicists have proposed other, more exotic forms of time travel that could, in principle, allow us to journey through time more dramatically. These scenarios typically involve extreme distortions of space-time that could create what physicists call closed time-like curves, paths through space-time that loop back on themselves, potentially allowing an object or person to arrive at an earlier time than when they departed. One of the most famous theoretical time travel mechanisms involves objects called wormholes. These hypothetical structures would be shortcuts through space-time, connecting distant regions of the universe through tunnels in the fabric of space and time itself. Imagine space-time as a sheet of paper, and suppose you wanted to travel from one edge of the paper to the other. Normally, you would have to travel across the entire surface of the paper. But if you could fold the paper and poke a hole through both layers, you could create a shortcut that would allow you to travel between the 2 points much more quickly. A wormhole would work similarly, creating a tunnel through space-time that could connect distant regions of the universe or potentially different times. If one end of a wormhole could be accelerated to high speed or placed in a strong gravitational field, the effects of time dilation could cause the two ends to experience time at different rates. This could potentially create a time machine, where entering one end of the wormhole could bring you out at an earlier time from the other end. However, wormholes face enormous theoretical and practical challenges. Most solutions to Einstein's equations that describe wormholes require exotic matter with negative energy density to keep the wormhole stable and traversable. Such exotic matter has never been observed and may not exist in nature. Even if wormholes could exist, they would likely be incredibly unstable, collapsing before anything could travel through them. Another theoretical possibility for time travel involves rotating black holes, also known as Kerr black holes. When a massive star collapses to form a black hole, any rotation the star had will be preserved and amplified, creating a spinning black hole that drags space-time around with it. This effect, called frame dragging, creates regions near the black hole where the normal structure of space-time becomes highly distorted. In the extreme environment near a rotating black hole, there could exist closed time-like curves that would allow an object to travel through time. However, these paths would require traveling through regions of space with such intense gravitational fields and radiation that any physical object would be destroyed long before it could complete its time-traveling journey. Some theoretical physicists have proposed even more exotic scenarios involving cosmic strings, hypothetical one-dimensional defects in space-time that could have formed during the early universe. If two cosmic strings were moving past each other at high speed, they could potentially create closed time-like curves that would allow time travel. However, cosmic strings are purely theoretical objects that have never been observed, and even if they exist, they would likely be incredibly rare and difficult to access. The possibility of traveling faster than light has also been proposed as a potential time travel mechanism. We have learned that the speed of light represents the cosmic speed limit, and that nothing with mass can travel faster than light. However, some theoretical proposals suggest ways that space itself could be manipulated to achieve effective faster-than-light travel without actually violating the speed limit. The Alcubierre drive, proposed by physicist Miguel Alcubierre in 1994, would work by contracting space in front of a spacecraft and expanding space behind it, allowing the ship to ride a wave of distorted space-time at effective speeds faster than light. While the spacecraft itself would never exceed the speed of light locally, it could potentially travel between distant points faster than light could travel through normal space. However, the Alcubierre drive faces similar challenges to wormholes, requiring exotic matter with negative energy density to function. Additionally, recent calculations suggest that the energy requirements for such a drive would be enormous, possibly requiring more energy than exists in the observable universe. Even if such technology were possible, it might create causality paradoxes if used for time travel. All of these theoretical time travel mechanisms face a fundamental challenge known as the causality problem. If time travel to the past were possible, it could potentially create paradoxes that violate the logical structure of cause and effect. The most famous of these is the grandfather paradox, where a time traveler goes back in time and prevents their own grandfather from meeting their grandmother, thus preventing their own birth and creating a logical contradiction. If the time traveler prevents their own birth, then they could not have existed to travel back in time in the first place. But if they never traveled back in time, then their grandfather would have met their grandmother. They would have been born, and they could have traveled back in time after all. This creates an endless logical loop with no consistent resolution. The grandfather paradox illustrates a deeper problem with time travel to the past. It could potentially allow effects to precede their causes, violating one of the fundamental principles of physics. In our normal experience, causes always precede effects. You must light a match before it can start a fire. You must send a radio signal before it can be received. This ordering of cause and effect is essential for the logical structure of the universe as we understand it. Some physicists have proposed solutions to these paradoxes. One possibility is the many worlds interpretation, which suggests that time travel to the past would create alternate timelines or parallel universes. In this scenario, when a time traveler goes back and changes something, they create a new branch of reality separate from their original timeline. This would allow changes to occur without creating paradoxes, but it would also mean that the time traveler could never return to their original timeline. Another proposed solution is the Novikov self-consistency principle, named after physicist Igor Novikov. This principle suggests that the laws of physics would somehow conspire to prevent paradoxes from occurring. If someone tried to go back in time and change the past, something would always happen to prevent them from succeeding. The universe would be self-consistent, with events unfolding in the only way that is logically possible. Some physicists have even suggested that the universe might have a built-in protection mechanism against time travel paradoxes. Stephen Hawking proposed what he called the chronology protection conjecture, which suggests that the laws of physics prevent the formation of closed time-like curves, except possibly on microscopic scales. This would mean that nature itself conspires to prevent time travel to the past from occurring. The relationship between time travel and the speed of light becomes even more complex when we consider quantum mechanics. At the quantum level, particles can exhibit strange behaviors that seem to violate our normal understanding of cause and effect. Virtual particles can appear and disappear in ways that seem to allow information to travel backward in time, though this information cannot be used to send messages to the past. Recent experiments in quantum mechanics have even demonstrated what physicists call quantum entanglement, where particles can be connected in ways that allow instantaneous correlations across arbitrary distances. While these quantum effects cannot be used to send information faster than light or to travel through time, they reveal that the relationship between space, time, and causality is even stranger than Einstein's relativity suggested. The more we study the fundamental nature of space and time, the more we realize how deeply interconnected they are with light and causality. The speed of light is not just a random cosmic speed limit, but a fundamental feature of space-time that determines how cause and effect propagate through the universe. Any attempt to travel through time must grapple with this fundamental connection between light, space, and time. Perhaps the most profound lesson from studying time travel is that it reveals the deep structure of space-time itself. The fact that time travel to the past seems to create insurmountable paradoxes suggests that there is something fundamental about the forward flow of time that we do not yet fully understand. Time appears to have a preferred direction, an arrow that points from past to future, and this arrow seems to be built into the very fabric of the universe. If time is always a journey into the past when we observe distant objects, what happens when we attempt to travel through it more deliberately? The answer, according to our current understanding of physics, is that we encounter fundamental barriers built into the structure of space-time itself. Could we break the laws of causality, or is time a path we can never escape? The evidence suggests that while we can slow down our passage through time by traveling at high speeds or in strong gravitational fields, and while we can observe the past by looking at distant objects, we cannot easily escape the forward flow of time or travel to arbitrary moments in the past. Time appears to be a one-way street, with the speed of light serving as both our window into the past and the guardian that prevents us from returning to it. As we contemplate the possibilities and paradoxes of time travel, we are reminded that the universe is governed by deep and beautiful principles that connect space, time, light, and causality in ways that we are only beginning to understand. The speed of light is not just a speed, but a fundamental feature of reality that shapes everything from our observations of distant galaxies to the very possibility of time travel itself. As we near the end of our cosmic journey through space and time, guided by the ancient light of distant stars and galaxies, we turn our attention toward the future. What new discoveries await us as we continue to push the boundaries of our ability to observe the universe? How might advancing technology allow us to peer even deeper into cosmic history, perhaps revealing new layers of the past that are currently beyond our reach? And what fundamental questions about light, time, and the nature of reality might we finally answer in the years and decades to come? The story of astronomy has always been the story of building better eyes to see the universe. From the first simple telescopes that revealed the moons of Jupiter and the phases of Venus, to the massive ground-based observatories that can detect the faintest whispers of light from the most distant galaxies, each advance in technology has opened new windows into cosmic history. Today, we stand on the threshold of a new era of astronomical discovery, with revolutionary instruments that promise to transform our understanding of light, time, and the evolution of the universe. The James Webb Space Telescope, which began operations in 2022, represents perhaps the most significant leap forward in our ability to observe the distant universe since the original Hubble Space Telescope. Unlike Hubble, which primarily observes invisible light, the James Webb Space Telescope is designed to detect infrared radiation, allowing it to see through cosmic dust and observe objects whose light has been redshifted by the expansion of the universe into longer infrared wavelengths. This capability is revolutionary because it allows us to observe some of the most distant and ancient objects in the universe. The first galaxies that formed after the cosmic dark ages emitted their light in the ultraviolet and visible portions of the spectrum. But after traveling for over 13 billion years through expanding space, this light has been stretched into the infrared. The James Webb Space Telescope can detect this ancient light, potentially showing us galaxies as they appeared when the universe was less than 400 million years old. These observations could reveal the formation of the very first stars and galaxies, helping us understand how the smooth, simple universe, revealed by the cosmic microwave background, evolved into the rich, complex cosmos we observe today. We might witness the moment when the first massive stars ignited, ending the cosmic dark ages and beginning the process of reionization that made the universe transparent to starlight. We could observe the assembly of the first galaxy clusters, the birth of supermassive black holes, and the emergence of the large-scale structure that defines the cosmic web. The James Webb Space Telescope might also help us study the atmospheres of exoplanets, distant worlds orbiting other stars. By analyzing the light that passes through these alien atmospheres, astronomers can determine their composition, temperature, and potentially even detect signs of biological activity. This could help us answer one of the most profound questions in science. Are we alone in the universe, or is life a common feature of cosmic evolution? But even the James Webb Space Telescope has limitations. There are regions of cosmic history that remain beyond its reach, epochs so early and so distant that even the most sensitive infrared observations cannot penetrate them. To push even further back in time, future telescopes will need to be even larger, more sensitive, and capable of observing at even longer wavelengths. Ground-based astronomy is also experiencing a revolution with the construction of extremely large telescopes. The 30-meter telescope, the Giant Magellan Telescope, and the Extremely Large Telescope will have collecting areas many times larger than current instruments, allowing them to gather more light and observe fainter, more distant objects. These telescopes will be equipped with advanced adaptive optic systems that can correct for the blurring effects of Earth's atmosphere, potentially achieving image quality that rivals or exceeds space-based telescopes. These giant telescopes will work in concert with space-based observatories to create unprecedented views of the universe. They will be able to study individual stars in distant galaxies, observe the formation of planetary systems around other stars, and potentially even detect the light from planets orbiting in the habitable zones of nearby star systems. Combined with advances in detector technology and data analysis techniques, these instruments could reveal cosmic phenomena that we cannot even imagine today. One of the most exciting frontiers involves the detection of gravitational waves, ripples in space-time itself that are created by some of the most violent events in the universe. Unlike light, which can be absorbed or scattered as it travels through space, gravitational waves pass through matter almost unimpeded, carrying information about cosmic events that might be completely hidden from traditional light-based astronomy. The detection of gravitational waves has opened an entirely new way of observing the universe, one that is completely independent of light. When black holes merge, they create gravitational waves that carry information about the masses, spins, and orbital characteristics of the colliding objects. When neutron stars collide, they create both gravitational waves and electromagnetic radiation, allowing astronomers to study these events with multiple types of observations simultaneously. Future gravitational wave detectors, including space-based instruments like the proposed Laser Interferometer Space Antenna, could detect gravitational waves from the earliest moments of the universe, potentially revealing information about cosmic inflation, the formation of primordial black holes, and other phenomena from the very beginning of time. These observations could complement our light-based studies of cosmic history, providing an independent way to study the evolution of the universe. The field of multi-messenger astronomy, which combines observations of light, gravitational waves, and other cosmic messengers like neutrinos, is revolutionizing our understanding of cosmic events. When astronomers can observe the same event using multiple types of signals, they can learn far more than would be possible from any single type of observation alone. This approach has already led to breakthroughs in understanding neutron star mergers, gamma-ray bursts, and other high-energy phenomena. Advances in artificial intelligence and machine learning are also transforming how we analyze the vast amounts of data collected by modern telescopes. These techniques can identify patterns in cosmic data that would be impossible for humans to detect, potentially revealing new types of cosmic objects or phenomena that we have not yet recognized. Machine learning algorithms can process the light from millions of stars simultaneously, searching for subtle variations that might indicate the presence of orbiting planets, stellar companions, or other interesting phenomena. The development of quantum technologies could also revolutionize our ability to observe the universe. Quantum sensors could achieve unprecedented sensitivity, potentially allowing us to detect gravitational waves from the Big Bang itself, or observe quantum effects in the cosmic microwave background radiation. Quantum communication networks could connect telescopes around the world or even in space, creating virtual telescopes with baselines larger than Earth itself. One of the most ambitious future projects involves the search for life beyond Earth. As our ability to study exoplanet atmospheres improves, we might detect biosignatures, chemical signs of biological activity in the atmospheres of distant worlds. The detection of oxygen, methane, water vapor, and other molecules associated with life could provide the first evidence that we are not alone in the universe. But perhaps even more profound would be the detection of techno-signatures, signs of intelligent technological civilizations. Advanced civilizations might leave detectable signatures in the form of artificial lights on the night side of planets, atmospheric pollution from industrial activity, or even megastructures built around stars to harness their energy. The search for such signatures represents a new frontier in astronomy, one that could transform our understanding of intelligence and civilization in the universe. The study of dark matter and dark energy, which together comprise about 95% of the universe, remains one of the greatest challenges in modern physics. Future observations might finally reveal the nature of these mysterious components of the cosmos. New telescopes could map the distribution of dark matter by observing how its gravity affects the light from distant galaxies. Space-based missions could search for the subtle effects of dark energy on the expansion of the universe, potentially revealing whether this mysterious force is constant or changing over time. The quest for a deeper understanding of fundamental physics continues to drive astronomical research. Future observations might test Einstein's theory of general relativity in new regimes, potentially revealing deviations that could point toward new physics. The study of black holes, neutron stars, and other extreme objects could reveal new insights into the nature of space, time, and gravity. As we develop new technologies and techniques for observing the universe, we are also developing new theoretical frameworks for understanding what we observe. The relationship between quantum mechanics and gravity remains one of the greatest unsolved problems in physics. Future observations of black holes, the cosmic microwave background, and other extreme environments might provide the data needed to develop a theory of quantum gravity that unifies our understanding of the very large and the very small. The future of astronomy also involves new ways of thinking about time itself. As we push deeper into cosmic history, we approach fundamental limits imposed by the nature of space-time. The cosmic microwave background represents the earliest light we can observe, but there may be other ways to study even earlier epochs. Gravitational waves from cosmic inflation, primordial magnetic fields, or relics of quantum fluctuations from the earliest moments of the universe might provide windows into times that are forever hidden from light-based observations. The possibility of detecting signals from parallel universes or other dimensions, while highly speculative, represents another frontier that future observations might explore. Some theories of quantum gravity suggest that our universe might be one of many in a vast multiverse, and subtle effects of these other universes might be detectable in the cosmic microwave background or other astronomical observations. As we continue to push the boundaries of exploration and discovery, we continue to ask fundamental questions about our place in the universe. How can we perceive the universe more clearly? What will the next wave of technology reveal about light and time? How far back in cosmic history can we ultimately see? Are there fundamental limits to our ability to observe the universe? Or will advancing technology always open new windows into cosmic history? The answers to these questions will likely surprise us, as they have throughout the history of astronomy. Each new generation of telescopes and detectors has revealed aspects of the universe that previous generations could not have imagined. The future promises even more dramatic discoveries, potentially revealing the nature of dark matter and dark energy, the possibility of life beyond Earth, and the fundamental structure of space-time itself. As we stand on the threshold of these new discoveries, we can be certain that our understanding of light, time, and the universe will continue to evolve. The ancient light that has guided our cosmic journey will continue to carry new secrets across the vast distances of space, delivering them to future generations of astronomers who will decode their messages and add new chapters to the ever-growing story of cosmic history. What will the next wave of technology reveal about light and time? Only time itself will tell, but one thing is certain. The universe still holds countless mysteries, and the light from distant stars and galaxies will continue to be our guide as we explore the deepest questions about existence, time, and our place in the cosmic story that continues to unfold around us. As we reach the end of our cosmic journey through space and time, guided by the ancient light of distant stars and galaxies, we find ourselves profoundly changed by what we have discovered. We began this exploration with a simple observation that light takes time to travel across the vast distances of space. But this simple fact has led us on an extraordinary adventure through the deepest mysteries of existence, revealing that our universe is far more wonderful, strange, and beautiful than we could have ever imagined. Throughout this journey, we have traveled not just through space, but through time itself. We have seen how the finite speed of light creates a natural time machine that allows us to observe the cosmic past with every glance at the night sky. We have learned that distance equals time in the universe, and that looking farther into space means looking deeper into history. This profound realization has transformed our understanding of what it means to observe the cosmos and our place within it. We have learned that every time we look up at the night sky, we are not merely observing distant objects in space. We are witnessing the history of the universe itself, written in light across the cosmic darkness. Each photon that enters our eyes carries with it a message from the past, a snapshot of conditions that existed when and where that light was created. The stars we see tonight show us the universe as it was years, decades, centuries, and millennia ago. The galaxies we observe through telescopes reveal cosmic history stretching back billions of years, to times when the universe was young and very different from what we experience today. We have walked through the solar system and beyond, discovering that the sun appears to us as it was 8 minutes ago, that the nearest stars show us light that is years old, and that distant galaxies reveal themselves as they existed billions of years before Earth even formed. Each step of this journey has taken us further back in time, creating a layered view of cosmic history where every observation represents a different epoch in the evolution of the universe. We have walked through the solar system and beyond, discovering that the sun appears to us as it was 8 minutes ago, that the nearest stars show us light that is years old, and that distant galaxies reveal themselves as they existed billions of years before Earth even formed. Each step of this journey has taken us further back in time, creating a layered view of cosmic history where every observation represents a different epoch in the evolution of the universe. We have discovered that time itself is not the absolute, universal, flowing river that our everyday experience suggests. Instead, time is intimately connected with space and light, woven together into the fabric of space-time that forms the stage upon which all cosmic events unfold. The speed of light is not just a random cosmic constant, but a fundamental feature of reality that determines how information travels through the universe, how cause and effect propagate across space, and how different observers experience the passage of time. The speed of light has revealed itself to be the universal speed limit, the cosmic constant that connects space and time into the unified fabric Einstein called space-time. We have seen how this speed limit creates the delay that makes us perpetual observers of the past, and how it shapes the very nature of cause and effect throughout the universe. Nothing can travel faster than light, and this fundamental limit ensures that information, causality, and the very structure of reality follow rules that can be understood and predicted. The journey of light across cosmic distances has shown us that the universe has a history, a story of evolution and change that spans over 13 billion years. We have seen how the smooth, glowing plasma of the early universe gradually cooled and condensed to form the first atoms, allowing light to travel freely for the first time. We have witnessed the formation of the first stars and galaxies, the assembly of large-scale cosmic structures, and the ongoing expansion of space itself. Each epoch of cosmic history has left its signature in the light that surrounds us. The cosmic microwave background carries information from when the universe was only 380,000 years old, showing us the afterglow of creation itself. The light from the first galaxies reveals the cosmic dark ages ending as the first stars ignited and began to illuminate the universe. Closer to home, the light from nearby stars tells us about stellar evolution, planetary formation, and the chemical enrichment of the cosmos through billions of years of stellar nucleosynthesis. Through the cosmic microwave background, we have glimpsed the universe in its infancy, seeing it as it appeared when it was only 380,000 years old. This ancient radiation surrounds us at all times, a constant reminder of the universe's fiery birth and the moment when light first became free to travel across space. In this primordial glow, we find the seeds of all the large-scale structure we observe today. Tiny fluctuations that would eventually grow under the influence of gravity to become galaxies, stars, and planetary systems. Through the Hubble Deep Field and other deep sky observations, we have watched galaxies form and evolve over billions of years of cosmic time. We have seen how the universe has changed from a place dominated by small, irregular, actively star-forming galaxies to the mature cosmos we observe today, filled with large spiral and elliptical galaxies. These observations have revealed that galaxy formation is an ongoing process, with cosmic structures continuing to grow and evolve through mergers, star formation, and the complex interplay between dark matter, ordinary matter, and dark energy. Through our study of nearby stars and planets, we have learned how stellar systems like our own come into being and how the chemical elements necessary for life are forged in the nuclear fires of massive stars. We have discovered that the atoms in our bodies were created in the cores of stars that lived and died billions of years ago, connecting us intimately to the cosmic story of stellar evolution and chemical enrichment. We have explored the limits of observation, discovering that there are boundaries to what we can see and know about the universe. Black holes represent ultimate limits, regions where space-time becomes so curved that not even light can escape, creating cosmic horizons beyond which we can never see. The event horizons of black holes remind us that there are secrets in the universe that will forever remain hidden from our view, no matter how advanced our technology becomes. These cosmic boundaries reveal something profound about the nature of space and time themselves. They show us that even light, the fastest thing in the universe and our primary means of gathering information about the cosmos, has limits. There are places where light cannot go, regions where the very concepts of space and time break down, and boundaries beyond which no information can travel. These limits are not failures of our technology or understanding, but fundamental features of reality itself. We have grappled with the relativity of simultaneity, learning that there is no universal now that extends across space. Different observers, moving at different speeds through the universe, experience time differently and disagree about which distant events happen simultaneously. This has profound implications for our understanding of time, causality, and the nature of existence itself. The universe does not tick to a single cosmic clock, but instead reveals itself as a complex tapestry where the perception of time depends on motion, gravity, and the fundamental structure of space-time. This relativity of time means that the present moment is not a universal feature of the universe, but rather a subjective experience that depends on our reference frame. When we observe distant galaxies, we each construct our own slice through space-time, our own version of cosmic history based on our motion through space and our position in the gravitational field of the Earth and Sun. This personal nature of time adds another layer of wonder to our cosmic observations. reminding us that each perspective on the universe is unique and valuable. We have pondered the possibilities and paradoxes of time travel, discovering that while we are already time travelers in the sense that we observe the past through light, more dramatic forms of time travel face enormous theoretical and practical challenges. The structure of space-time itself seems to protect the logical consistency of cause and effect, preventing paradoxes that could undermine the rational order of the universe. Time appears to have a preferred direction, an arrow that points from past to future, and this arrow is built into the very foundations of physical reality. Time appears to have a preferred direction, an arrow that points from past to future, and this arrow is built into the very foundations of physical reality. Throughout this journey, we have been constantly reminded that we are part of the very story we are trying to understand. The atoms in our bodies were forged in the cores of ancient stars that died billions of years ago. The oxygen we breathe was created in massive stars through nuclear fusion and scattered into space when those stars exploded as supernovae. The carbon that forms the backbone of every molecule of life was cooked in the nuclear furnaces of intermediate mass stars and gently expelled into space through stellar winds. The iron in our blood was forged in the final moments of a massive star's life, in the incredible violence of a supernova explosion. We are literally made of star stuff, cosmic recycling at its most profound level. The calcium in our bones, the phosphorus in our DNA, the sodium and potassium that allow our neurons to fire and our thoughts to form, all of these elements were created in stars and delivered to Earth through billions of years of cosmic evolution. We are not separate from the universe we observe, but are instead its most recent creation, conscious arrangements of matter that have developed the remarkable ability to contemplate their own origins. The light we use to see the universe began its journey long before our solar system existed. When we observe distant galaxies, we are seeing light that started its journey when the universe was young and our corner of space was empty. That ancient light has traveled across expanding space for billions of years, carrying information about cosmic conditions that existed long before Earth formed, before the sun ignited, before our galaxy took its current shape. This creates a humbling and awe-inspiring perspective on our place in cosmic time. We exist for the briefest moment in the vast span of cosmic history, conscious sparks that flicker into existence and contemplate the universe for a few short decades before returning to the cosmic recycling that continues throughout space and time. Yet in that brief moment of consciousness, we have developed the ability to understand our cosmic heritage, to trace our origins back to the Big Bang itself, and to see our intimate connection to the stars and galaxies that fill the universe. Our planet Earth, the only world we know to harbour life, is itself a cosmic traveller carrying us through space and time. Earth orbits the Sun at 30 kilometers per second, and the Sun carries our entire solar system around the centre of the Milky Way at over 200 kilometers per second. Our galaxy itself is moving through space, part of a local group of galaxies that is being pulled toward a massive concentration of matter called the Great Attractor. We are passengers on a cosmic journey that began billions of years ago and will continue for billions of years into the future. The light from distant stars and galaxies continues to rain down upon us every night, carrying information about the cosmic past and delivering it to anyone who takes the time to look up and wonder. This ancient light connects us to the deepest history of the universe, reminding us that we are citizens of the cosmos, temporary arrangements of atoms that have somehow developed the remarkable ability to understand their place in space and time. Every night, the stars invite us to join in the cosmic conversation that has been going on for billions of years. The light we see tonight began its journey from distant suns at different times throughout cosmic history. Some photons left their sources when dinosaurs roamed the Earth, others when the first complex life was evolving in ancient oceans, still others when Earth was a molten ball of rock orbiting a young sun in a galaxy very different from the mature spiral we see today. This cosmic mail delivery system ensures that the night sky is always changing, always bringing us new messages from different epochs of cosmic history. The stars we see tonight are not the same as the stars our ancestors saw, not because the stars themselves have moved significantly, but because the light reaching us now left those stars at different times than the light our ancestors observed. We are each receiving our own unique selection of cosmic mail, our own personal view of the universe's past. As we have seen, our quest to understand light and time is far from over. New technologies promise to reveal even deeper layers of cosmic history, potentially showing us the very first stars and galaxies, the formation of the first planetary systems, and perhaps even signs of life beyond Earth. The James Webb Space Telescope and other advanced instruments are already pushing back the frontiers of the observable universe, revealing galaxies from when the cosmos was less than 400 million years old. Future observations might answer some of the most profound questions about the nature of dark matter and dark energy, the mysterious components that dominate the universe but remain largely invisible to our current instruments. We might discover the true nature of black holes, learn whether the universe will expand forever or eventually collapse back on itself, and find out if life is a common feature of cosmic evolution or a rare and precious occurrence limited to our own world. The possibility of detecting life beyond Earth remains one of the most exciting frontiers in astronomy. As we develop better techniques for studying the atmospheres of exoplanets, we might find chemical signatures of biological activity in the air of distant worlds. The detection of oxygen, water vapor, methane, and other molecules associated with life could provide the first evidence that we are not alone in the universe. Even more profound would be the discovery of intelligent life, civilizations that have developed technology and perhaps even learned to harness the energy of their stars. The search for techno-signatures, artificial signals or structures created by advanced civilizations, represents a new frontier that could transform our understanding of intelligence and consciousness in the universe. But perhaps the most important lesson from our cosmic journey is not about the specific facts we have learned, but about the sense of wonder and connection it inspires. When we understand that the light reaching our eyes tonight began its journey millions or billions of years ago, we gain a new perspective on our place in the universe. We realize that we are part of an ongoing cosmic story that stretches from the Big Bang to the present moment and will continue long into the future. This perspective transforms how we think about our daily lives and our relationships with each other and with the natural world. We are all fellow travelers on a cosmic journey, temporary arrangements of star stuff that have developed consciousness and the ability to contemplate the universe that created us. Our differences, which often seem so important, pale in comparison to our shared cosmic heritage and our common origin in the hearts of ancient stars. The universe reveals itself to us gradually, one photon at a time, through the patient work of astronomers and the accumulated observations of countless individuals who have looked up at the night sky and wondered about what they were seeing. Each observation adds another piece to our understanding of cosmic history, another thread to the tapestry of knowledge that we are weaving together as a species. This collaborative effort to understand the universe spans cultures, continents, and centuries. Ancient astronomers in Babylon and Greece laid the foundations for our understanding of planetary motion. Medieval Islamic scholars preserved and expanded upon this knowledge during Europe's Dark Ages. Renaissance astronomers like Galileo and Kepler revolutionized our understanding of the solar system. Modern astronomers using space-based telescopes and gravitational wave detectors continue to push the boundaries of cosmic knowledge. Each generation builds upon the work of those who came before, adding new observations, developing new theories, and asking new questions about the nature of space, time, and existence. We are part of this grand human endeavor to understand our place in the cosmos, and future generations will build upon our discoveries to reach even deeper into the mysteries of the universe. Tonight, when you step outside and look up at the stars, remember that you are seeing ancient light that has traveled across unimaginable distances to reach your eyes. You are witnessing cosmic history, observing events that happened when the universe was younger and very different from what we know today. You are participating in the greatest adventure possible, the quest to understand our origins, our place in the cosmos, and the nature of existence itself. Every star you see represents a sun that may have planets orbiting around it. Every galaxy contains billions of stars, each with the potential to harbor worlds where the same questions about light and time might be pondered by other conscious beings. The universe is vast beyond imagination, filled with countless worlds and the potential for countless stories of discovery and wonder. Perhaps somewhere, in a distant galaxy whose light is just now reaching Earth after billions of years of travel, there are beings looking up at their own night sky and contemplating the same questions we are exploring tonight. They might be seeing our galaxy as it appeared billions of years ago, when it was younger and more actively forming stars. They might be wondering, as we are, about the nature of time and light, about their place in the cosmic story, and about the possibility of other conscious beings in the universe. This possibility adds another layer of wonder to our cosmic contemplations. We might not be alone in our quest to understand the universe. Across the vast distances of space and time, other minds might be engaged in the same process of discovery, asking similar questions and perhaps finding different answers. The light that connects us to the cosmic past might also connect us across unimaginable distances to other conscious beings who share our sense of wonder about existence. Rest now beneath the ancient light of distant stars, knowing that you are part of the cosmic story that continues to unfold around us. The universe is more than just the present moment. It is the past, preserved in light and delivered across space. It is the present, unfolding in countless worlds and systems throughout the galaxy. And it is the future, full of possibilities and discoveries that await the next generation of cosmic explorers. The light that surrounds us carries the memory of 13 billion years of cosmic evolution. In that ancient radiance, we find not just the history of stars and galaxies, but the story of how matter and energy, space and time, came together to create a universe capable of producing conscious beings who can look back through time and understand their own cosmic heritage. As you drift off to sleep under the starlight, let yourself be carried by the cosmic currents that flow through space and time. You are part of the universe's long journey toward complexity and consciousness, a brief but magnificent flowering of matter and energy that has somehow learned to contemplate its own existence. Tomorrow, the cosmic story will continue, bringing new light across the vast distances of space, carrying new messages from the depths of time, and offering new opportunities for wonder and discovery. Sleep peacefully under the starlight, knowing that every photon touching your skin is a messenger from the depths of space and time, connecting you to the vast cosmic story of which you are an eternal part. The universe continues its patient expansion, carrying new light across ever greater distances, preserving the memory of each moment and delivering it to future observers who will continue the endless quest to understand the mysteries of existence. In the end, our exploration of light and time has revealed that we are not just observers of the universe, but participants in its ongoing story. We are the universe becoming conscious of itself, developing the ability to look back through time and understand its own history. Every time we look up at the stars, we are the cosmos contemplating its own past, present and future, written in the ancient language of light across the infinite darkness of space. The cosmic journey continues, carrying us forward through space and time, while the ancient light of distant stars continues to whisper the secrets of the universe to all who take the time to listen. Sweet dreams, fellow cosmic travelers, and may your rest be filled with the peaceful glow of starlight and the gentle rhythm of the cosmos breathing around us through the endless night.